In this video, we are going to present a few examples of the autoregressive models. So the first one is fully feasible sigmoid belief network. A belief network is very popular, uh, perhaps in 2010-ish. Um, it is less popular right now, I guess, for some reasons. However, this example shows that no matter what the backbone or the framework or implementation that you are using, autoregressive is a good idea of a very general idea that you can use any specific implementation or specific architectures. So in this example, the implication is using the autoregressive and the belief network architecture on generating MNIST images. MNIST is handwritten digits. It has a preprocessing that make it to be a binarize the image. So it only has a black and white part. So the left one is the generated image. It looks pretty good. The real MNIST one doesn't look like it because it has not. Usually we see something that is not binarized. But if we binarize the digits, we can imagine that this would be something that should be look like. So this one I'll consider it pretty good. The right one is because we are using autoregressive model. It has some, you can extract the probability distribution from the density from the models. So this one indicate, although the output is binary, it can output the distributions, the probability of whether it would be 0 or 1, the probability of it. So you can see it's kind of more blur. It has some gray, not just black and white, some gray in it to indicate that is probably not 0 and 1. But MNIST is considered to be a pretty simple dataset. So by using it on a more complicated dataset, Caltech Seahawk dataset. So the left one is the sample from the training data. The right one is some kind of average of the generated things. It's kind of more like the probability distribution one, but not exactly. So you can see that in this case, the generated image is compared to the MNIST one is less, the quality is less impressive. So, but still, it can do something as complicated as image generation. Another example is a neural autoregressive distribution estimation. So you can see that it is still, you can see that there are 784, so it is still working, intent to work on something that is 28 by 28, an image generation like this one. So basically it is enumerate or sort the pixels one by one, maybe from the top to bottom, left to right, and consider all pixels as a sequence. So you can see that we use the previous pixels, the value from pixel values to predict the next one. So the this one is also has just one layer, one hidden layer. So the architecture might be a little bit easier. If you consider a more hidden layer, you might want to it will make the architecture more complicated. So you might to think a little bit carefully to make sure that everything is only dependent on the previous ones, not the future ones, not the later ones. So it's pretty straightforward for using a neural network to generate the output. Um, in the same paper, it is a 1916 paper, I think, I believe, and it also consider in the same paper it also consider a convolution, not only just the MLT one. It also consider the convolution one and the deep one. And like the uh, fully feasible sigmoid belief net, it also consider only the binarized MNIST. So the left one is the generated sample, and the right one is the probability, just like what we have seen in for the fully feasible sigmoid belief net. But the same thing can be pretty much the similar thing can do if we replace the belief net with a MLP or a convolutional neural network. So another kind of immediate application is for language generation. So we are consider a character language model. So in contrast with like the word language model or a token language model like the ChatGPT or more modern models, it only consider letters, characters, only alphabets. So for example, we can consider each like x1, x2, x3, x4, each one as a character. So if the first character is H, when training, we wish it to output an E because our training data is hello, or not hello because there's O here. Obviously, there's O here. It doesn't meant to have a hell. It has a hello. So if this is a hello is our training data. When doing the training, we get the first input H, and we are expecting to have an output E, or at least we are trying to train it to have an output E. And after we have the second character HE, we are hoping this model to output an L. Now, this model is also an RNN model because this one has a hidden layer passed through this kind of things. So we are going to talk about this model in more details, and before that, we are going to talk about some basic idea and introduce what RNN is. So the similar things we can not only can we can work um, characters or like in a text data, we can also work on uh, pretty much work on image data. Except image data is more usually more complicated and a little bit not so nature. What I mean is that if you consider a pixel right here, each pixel, of course, we first we don't have a natural order. I mean, a natural linear order of these pixels. We know we probably want it from the top to down, top to bottom, left to right. However, should we go like a line by line or like a zigzag things like this one? It's not obvious. There's no obviously one best choice. So we might want to try and see what happened. And the other thing is each pixel is not just single element. each pixel contains like RGB 3 channels. So we probably need to arrange it like red, green, blue, red, green, blue, given that we already have the order of the pixels. However, why the red should be ahead in front of green, why the blue should be the last one? It is kind of strange. So uh, if not strange, it's kind of arbitrary. It's kind of arbitrary. So if you are a designer, it might make you a little bit uncomfortable, but still, maybe the order doesn't matter that much, so it may still worth a try. There are other alternatives that I can think of, but this I don't think there is no obvious one best design choice. So there are a lot of different uh, decision you need to make. A lot of different compromise you need to make. There are no single one best choice. That makes this one less natural than the case that like a character language model. So, but we already done this before. Like we have already done this in the this one neural autoregressive distribution estimation and the sigmoid belief network. We have already done this one before. So that at least somebody has already successed. And one more thing is that how do we actually model the intensity of a pixel? We know that in in this case we actually have binarized the value from 0 to 1. It is okay because we only have two categories, so it is simple, just a probability of being 1 or 0. So this actually is a workaround for many issues that happens to the images. Of course, we still have an issue that we don't have a natural order of the pixels, but we don't have the channels. We only have one channel, so that one less problem and one less issues, and we actually binarize the intensity into a category, so that becomes a non-issue. However, in this case, we are still in we cannot actually do the binarize. Otherwise, if we do the binarize, the picture will be look very oval, because we have each channel becomes a full green or full or zero or not green at all, and another channel is the full red or not red at all. It will make the picture only have like 8 colors, so it will look pretty oval. So we still decide to keep the 256 level of intensity of each channel. So however, how do we do that? So in fact, it actually does is using a discrete model to fill all this 0 to 250 as a discrete. Like we said before, we the intensity is actually something that has a structure, a topological structure, because we know that it is there are some greater value, greater numbers and lower numbers. So if the intensity is indeed like 200, if our prediction is like 199 or 201, then it would be good, pretty much good enough, because it can be very hard to tell a difference between 200 and 201 by a naked eye. So it is in fact the one that with topology on this value. However, I believe this one is actually used. I kind of my memory is kind of faded, so I'm not entirely sure. But if I remember correctly, they are using each value like a discrete space. So it actually has 0, 1, 2, 3, 4, 255 as discrete tokens, and use cross entropy to do the prediction. I'm not entirely sure. Okay? That is what I remember, but right now I'm not so confident about my memory. Okay, so if we do this one, it's certainly we will imagine that it might work, and we are expected it to work if you're doing everything correct, like the conversion is or design the architecture correct. We're not surprised it will work, even though it has some weakness or issues that we just mentioned, potential issues that we just mentioned. And in fact, it does work and a little bit better than expected. So it works pretty good. This one is RNN because it uses the LSTM or GRU. I don't remember, but it uses RNN to do so. So in these cases, it's given the above half of the image it was given, and it used auto completion. And after it generated one pixel and use this pixel as an input and predict the next one, and use the newly generated, append the newly generated into the input and predict the next one, and so on. So it can complete the whole image. So you can see the generated image seems okay. It also has, in the same paper, it also has a version of using the CNN neural network. Just I would say that CNN is pretty good. It's pretty similar, actually, pretty similar compared to the RNN, and it's actually faster when you train it, and it can be done because if you are training it using an RNN, you have to do it pixel by pixel. But by using CNN, if you do it correctly, when I said correctly is you have to prevent the everything to see the future elements, because you see that the CNN has a kernel, convolution has a convolution kernel, it is a square sized. So if you don't do anything, if you don't modify anything, at least for the two-dimensional case, it's kind of difficult to ensure that everything, your output is only dependent on the past value. Yeah, there are some future value that is toward the button and the right. Those things are considered as the future because we are consider our pixel, generated pixel is in the center of the kernel, which is a square size thing. It's the center in the center of the square. So if you don't modify anything, it will see the future. So you have to do something to prevent the pixel to see in the future. Not only the spatial, because the RGB is in a channel. So you have, so the future exists in the same pixel and in different in the same pixel but in a different channels. So that makes things more complicated. You can imagine. We're going to talk about details later, maybe next week, I guess. But you can imagine there are a lot of difficulty. So however, it can train more faster. So in the orange paper, the pixel CNN is not does not produce the image as good as pixel RNN. However, in probably the next one paper, these papers are written by the OpenAI guys. They do the auto-regression things for a very long time. They are stick with this approach, and you can see their success time. I mean, ChatGPT is a very good example that they are really success. They are doing a simple thing and doing it consistently, and finally they do it really good. But let's go back to Pixel CNN. So in the next video, I think they call it Pixel CNN Plus. So this one use uh, gated convolution with that is mimic some features as exist in the RN architecture and port it into the convolution architecture to improve the quality of the generated image, and it also faster, at least faster in when training. So we got the pixel CNN right here. So not only pixel CNN, but also they is also work from OpenAI. You probably has a difficulty to reach the page because it is buried really down into the many recent works provided by OpenAI. It used to have a major position in their website in the research. They list like 4 or 5 recent researches. Image GPT was there for quite a few times, like maybe half a year or 1 year. I don't remember. But right now it's kind of difficult to reach the page because you have to dig like the next page, probably 3 or 4 pages away from the first one, and you can find this guy. This one is used to be one of the major achievement and the famous achievement, but because we have Sora, we have DALL-E 2, DALL-E 3 right now, so it's people kind of let's talk about it. Really talk about recently. But you can see it works pretty much like the Pixel CN, Pixel RM, except it's using a GPT, which is a transformer architecture. So just like the Pixel RNN and the GPT, it can embed text. I mean, encoding text and images in the same space, same letter space. Because you can see that although the example here is the image completion, but you can imagine if we encode some English sentences or natural language sentences in front of this image, like a description of this image, then we can generate this image according to the description of these sentences. It is possible to do so because it is just an autoregressive model. It is auto-completion, like we said before. It's just an auto-completion. No matter what you give it, it will learn. So if your training data is a description and followed by image that is consistent with the description, then it will learn about that. Not only it will complete the image, it will complete the sentence by a image that is consistent with the sentence. The image quality is not as good. It is still in the GAN era. So the image quality is okay, but not that impressive. So if that was Sora kind of quality, Sora is a big leap from, I mean, we only know that a lot of video text to video generation is so good and improve advanced really rapidly. The stable diffusion video and like the Pika and even the animative is all really good. Especially the stable diffusion video was kind of impressive back to when it was announced or published. But Sora, not image GPT, Sora was a really huge leap. Image GPT is something really good, but not that surprising because compared to the advance of GAN at that time. It was okay, had some nice properties, but not the quality is not difference is not that huge. Okay, so that is image GPT, and not only we can generate text and images, like we said, the text is more natural fit to autoregressive model. Image is a little bit not so natural, but it still can work just fine. However, we can also work on audios. Audios are also a perfect fit for autoregressive models because audios can be considered as a time series. It is a time series if you consider the phase at least in the wave space. However, it is kind of difficult because usually the audio has a very high frequency. In a typical audio files, it is recorded in like 48 kilohertz. So in 1 second, it is a time series of a length of 48,000. 48,000, that is quite long. So if you consider like an image, like a convolution on image, we usually use a kernel like 3x3, 5x5. If you wish to reach, I mean, if you can actually imagine that the audio is the current volume of this audio may be relevant, correlated to the audio, the sound, like in half a second before, or maybe 1/10 of a second before. But that was really, really long. You can very difficult to reach that by a kernel size, a window size by 3, even if you use a certain stride or a few layers. It will have a very hard time to actually let the sound that happened, the element that was 2000 index away to actually have some impact on the current sample. So it's very difficult to do so. So in fact, when people doing audio generation, even when we do using the deep neural network, people are usually first transform the audios into a spectral domain, typically transform into a male spectrum. So the frequency is not that high. So people will handle that using like convolutional neural network or other kind of things. However, WaveNet introduced a method that directly using the convolution deep learning neural network on the wave or spatial space. So basically, it is simply a autoregressive model, but it's called the causal convolution. It means we only this guy only affected by the previous samples. So we only use we don't use the future ones. We only use the things that already happened. We already observed so far. If you consider this as a time series, we don't use future samples for every generated or every outcome. We only use something that already happened so far. We already observed at the time being. So that is not too difficult. It only has a different name called the causal convolution, but basically it's just using convolution on just autoregressive convolution models. Basically, but we have a name that called the causal convolutions because the future will not affect the past. So it is pretty straightforward because it doesn't have the issue that like what we were doing for images, because image has a two-dimensional layout. It only has a one-dimensional layout. So there's no choice from whether we should go from left to right, then top to bottom, or from or other way around, like from the left to from top to bottom, then left to right, or doing some like a zigzag way of generating things. We don't have to worry about that. It has only just one dimension or only one way. The only difficulty is the relevant context window is really long. So if we are only considering using the convolution or even recurrent neural network, it cannot handle the correlation for the length like 1000, 2000 long. It's just too long. So how do we do that? It used dilated convolution to handle this issue, to manage this issue. Basically, because we know that we need a really long context window, so we don't actually need to consider all the effect of the past 1000 element or 2000 element directly. We can first do a sample that jump, do a long jump to this guy. So if we want to generate the current output, then first we consider the current output of the last layer, and consider the output like half a second ago, 0.5 seconds ago of the last layer. And in this layer, we consider maybe 0.25 or 1/4 seconds ago, and the current one. And for this layer, it consider the current effect and the outcome of 1s ago, and so on. So because of this one, it will eventually consider, I mean, if every sample happens in the last like half a second, it will all somehow more or less in fact affect the result of this outcome, but we can do it more efficiently. So that is called a dilated causal convolutional layers. The causal one is essential because we all need it. Dilated because we are trying to do this more efficiently. So it turns out WaveNet can handle the things more easily. However, I think currently people are using transformer because transformer can also do that, and bypass the, I mean, can consider the long time effect. But still, this one is pretty interesting, and the idea is, it demonstrates that the idea is straightforward, but if you really want to implement it, you will consider a lot of technical difficulties, and there are many ways, and it's kind of interesting to bypass and solve these issues in order to, and you will have some compromise, definitely, because there's no things that can be all good. So you will have some compromise, but it is, if you know what they are doing, it is always doable. Okay, so that's a few examples that we present in this video. We're going to talk more details in a few examples before, mostly for the character-based language model and Pixel CNN and Pixel RNN.